a ladder 25 feet long is leaning against the wall of the house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. Okay, so we got a related rates problem here and a variety of questions. So let's take a look. What is the velocity of the top ladder when the base is given below? Okay, so when it's 7 feet from the wall. So basically for this first part, what we're going to do, first we got to set up our relationship between our measured values, the distances here of that right triangle. So they're calling this, or I'm just going to say x squared plus y squared equals 25 squared. So I'm calling this x and this distance here y. Those are changing. Those are varying as the ladder gets pulled away from the wall. So that's my setup for this first question, because it says, what is the velocity of the top ladder when the base is given below? So like how fast, or what's the velocity for the top of the ladder? How fast is it moving in the down direction? So if we take the derivative with respect to time, both sides of the equation, we should have that, right? Derivative of 25 squared is 0, constant. And then what we're going to do is just plug in the values in order to find what they're asking for, which should be dy dt. Okay, so that's the velocity of the top of the ladder, how fast that's moving there. So basically we should have enough information to answer the question. That is, I should be able to plug in x, dx dt, and y, or if I don't have them, I should be able to find them. So let's try and do that. 7 feet from the wall, that's x, so that's 2 times 7. We know the rate that x is moving, that's a positive 2. X is increasing. 2y dy dt. And our goal is to find dy dt, so we should have a value for everything else. These 2's we could have divided by, but that's okay. We just need a value for y. Okay, so at this moment in time, the ladder is always 25 feet. We are 7 feet from the wall at this moment in time. Okay, so we could find the distance y by Pythagorean theorem. So that is going to give us 25 squared minus 7 squared equals y squared. And you might recognize that triangle as a Pythagorean triple. And if you do that, you should get for your answer 24. Okay, so there is dy dt. I'm going to subtract that value and then divide by that value, right? So the rate at which the top of the ladder is changing, dy dt is, that's going to be negative 28. And this should be 48. And that will give you your answer. 14 over 24, 7 over 12, I believe. And the unit would be feet per second. Okay, so that is the process for the part A. These other two questions work the same way, so let's look at these other ones. There was area of the triangle is changing when the base ladder is 20 feet from the wall. Okay, so for part B, we got area questions. Area of a triangle is 1/2 times the base times the height, which in the picture I called x and y. Okay, so now that's our first step. I like to kind of do these in 3 steps. Step 1, write your equation out. Step 2, figure out what was given. So given rate is, find the rate at which the area of the triangle is changing when the ladder is 20 feet from the wall. So the given rate would be dx dt. I didn't do this in the first one. I probably should have set up our work, organize ourselves. Given rate dx dt equals 2. And then what we want to do is find dA dt. when what? Find the rate at which the area of the triangle changes when the base of the ladder is 20. So when x is 20, and we could find y at that moment in time too, because we know that the hypotenuse is 25, right? So at that moment in time, we can maybe get this out of the way first instead of later like we did the first time. So this should be 25. This is when they're interested in, and this is also Pythagorean triple. This is a similar triangle to a 3, 4, 5. So this should be, if you divide them all by 5, that's 5, that's 4, so this should be 3 times 5. So that side should be 15, okay? Now, so if you look at what we got, so we organized ourselves a little bit better on this one than I did the first one. We're going to take, the goal is to take the derivative of this with respect to time, okay? So we might try and foresee an issue that the idea is to take a look, and when I take the derivative of this, what are my unknowns going to be? Am I going to be able to fill in everything with what's given down here? If you take the derivative of this, you'll have a dA dt on this side. Over here, you're going to have x's and y's and a dx dt and a dy dt. So we have an issue there that we won't have a solution for dy dt. We won't have a value for dy dt. So that could be a problem, and I'll show you what I mean. If we went ahead and did the calculus step, dA dt equals 1/2, and then you need the product rule, so be careful, right? So you have to do leave x alone dy dt plus leave y alone dx dt. Okay, so we have, and this is why I like to organize myself like this. We got this. We know what these two values are. But we don't know the rate. Sorry, we don't know that one. We don't know dy dt. We know the value for x. So this is a problem, right? We're saying, well, I'm not too sure what dy dt is, and I can't answer the question without it. So what do? Well, if we go back to our relationship, consider the triangle formed by the side house, ladder, and the ground. Find the rate at which the area of the triangle is changing when the base. So the question would be, how could I figure out, maybe potentially rewrite the area formula as a function of a single variable? That would be helpful. In fact, if I could write as a function of x and only x, then when I end up with dx dt's, when I do the calculus, I'll know what they are. So that would be the question. So if I go back to my picture, now be careful, it's not this picture. This is just one moment in time. We need the variable picture, that is, as this triangle changes. This is always 25 because it's a ladder. That's not changing. But these two values are changing, right? So the idea here would be to try to, whoops, got those backwards, to try to sub out y, basically, is what we're doing, right? And you know this is true, x squared plus y squared equals 25 squared. So you could solve for y, 25 squared minus x squared. And then you take the square root, and we don't have to worry about the plus or minus because it's a positive value, right? Y and x are always positive. So we've achieved the goal. That was a little trick with that one. I had to replace y because I don't know what dy dt is, but I have a relationship between x and y, which will allow me to rewrite my area function as just a function of x, okay? So now I can suffer through the calculus piece. This would be 1/2 power, so I'm going to have to do the product rule here, leave x alone, take the derivative of this thing, 1/2, 25 squared minus x squared to the negative 1/2. Times the derivative of the input function with respect to time, so that should just be 2x dx dt, and that's got to be negative. And then I'm going to say plus, and then we take the derivative of the other function, the x, which is just 1, and then I'm going to have 25 squared minus x squared. under a root. 25 squared minus x squared. Sorry, that's kind of small. That is my derivative. Okay, so now I'm going to plug in all the values, and I should be able to get my solution that way. So let's see. And this is why I try and organize myself. If I go back up here, I know what dx dt is 2, and then I know what x is. It's 20. So let's see. X is 20. 20 times a half is 10. X is 20. So let's see, that's a negative 1/2. So let's try and clean this up a little bit. So I got a 10. I'm going to plug in 20 here, right? So I got the square root of, in the denominator, 25 squared minus 20 squared. That's going to have a perfect square, so that's nice. That's a negative 2x. Negative 2x. Dx dt is 2. And then this is 25 squared minus 20 squared. Okay, so I got a 1/2 times 40, 80, negative 800. All over. This should just be 15, right? It's basically the third side of the triangle for that moment in time. 25 squared minus 20 squared right here. 25 squared minus 20 squared is 15 squared. Square root is 15. And then same thing here, right? This should be 15. And my 1/2 is out here. And there's your answer. Whatever that reduces to is what you should get for your dA dt. That was a trick one. Let's go back. Let's review those two real quick. So the first one, pretty straightforward. We're talking about two distances, and you got a right triangle. So that is my step 1. And then step 2, I usually say dx dt equals 2. And then I say step 3, what I want to find, right? So I say find dy dt when, and then I fill in whatever I can, my given information. And we could have done these other two guys the same way. Part B was tricky, so here's my process. Same process. Step 1, here's the relationship, talking about area. So I write an area equation, relate the area. Given rate, again, same rate given, dx dt. And then I know what I want to find, dA dt when x is 20, y is 15. All right? So once I get that, then I do the calculus. In this one, I realized dy dt wasn't given, so I had to come up with this creative way to write to write y in terms of x.